The definition of the nth root. If n is any positive real integer, then the principal root of a is defined as the nth root of a to the nth power is equal to a. The real nth root has the same value as a, and if n is even, then the value of your radicand, a, must be greater than or equal to 0, so it must be positive. You need to pay special attention to the question. When evaluating or simplifying a radical, you are looking for the principal root. But when solving an equation, you want all possible solutions. In number 19, for example, all we're being asked to do is evaluate. So we're looking for the principal root. The principal root will have the same value as the radicand. So when we evaluate the square root of 49, this is going to be positive 7 because my radicand is positive. In number 20, we're being asked to solve. So that means we want all possible solutions. X squared equals 49. When we solve this, we need to take the square root of 49. But because we have to be equal to positive 49, we could potentially have a positive or a negative answer. The reason this happens is because negative 7 times negative 7 is 49, and positive 7 times positive 7 is also 49. So when you evaluate, you look for the principal root. When you solve, you look for all possible solutions. Just like exponents, roots have different properties as well. The product rule states that if you are multiplying two radicals together, and those two radicals have the same index, so n, for example, might be a square, so the square root times the square root, then you can combine those two radicands, what's inside your radical, underneath the same radical with the same root. So for example, let's say we're finding the square root of 6 times the square root of 6. Well, we have the same index, so we can find the square root of 6 times 6, which would be the square root of 36, which is 6. The quotient rule says that if you are dividing two radicals with the same index, then you can combine those two radicals under the same radical with the same index together. So for example, if we're finding the square root of 50 divided by the square root of 2, we can actually combine those into the square root of 50 over 2, which is the square root of 25, which is 5. When you're finding the root of a root, so let's say we're finding the nth root of the nth root of a. Well, this is the same as finding the n times nth root of a. So it's like raising a power to a power. You multiply the indexes together. So if I'm finding the square root of the square root of 16, well, this would be the fourth root of 16, which is 2. Or you can break it down as, I know the square root of 16 is 4, and the square root of 4 is 2. The nth root of the nth power. If we're taking the nth root of a to the nth power, the nth root of a to the nth power is equal to the absolute value of a if n is even. The nth root of a to the nth power is equal to whatever the value of a is if n is odd. So for example, if I'm taking the square root of -3 squared, the answer is +3 because it's the absolute value of what's inside. But if I'm taking the cube root of -5 cubed, then it is -5 because my n value is odd. True or false? The square root of 4 times 9 is equal to the square root of 4 times the square root of 9. Well, we can prove it. This is the square root of 36 is equal to the square root of 4 is 2, the square root of 9 is 3. The square root of 36 is 6, and 2 times 3 is 6. This is a demonstration of the product rule. And number 2, the square root of -4 over 9 is equal to the square root of -4 over the square root of 9. Well, this is a demonstration of the quotient rule, so it is also true. In number 23, we have the square root of 4 plus 9 is equal to the square root of 4 plus the square root of 9. Well, if you look at it from a proof perspective, 4 plus 9 is 13, so I have the square root of 13. This statement is saying that the square root of 13 is equal to the square root of 4 plus the square root of 9. But the square root of 13 is not equal to 6. So this is false. It's important to note that the product rule and the quotient rule does not apply to addition and subtraction. Let's try a few examples. When you are simplifying radical expressions, you are looking for the factor of the radicand. So x to the fourth can be broken down into x times x times x times x. If I'm taking the cube root of x to the fourth, then I am looking for an x cubed that lives inside. So this is the same as saying x cubed times x. We factor it down. The cube root of x cubed is x. When you take the cube root, it moves outside the radical. So this is x times the cube root of x. And number 25, the same thing. You are looking for the exponents that match the index, and you want to factor anything else that doesn't match. So with 162, if we factor this down, you can start as small as 2. So this becomes 2 times 81, and 81 becomes 9 times 9, and 9 becomes 3 times 3, and 3 times 3. So here's my set of 4. So 81 is a perfect fourth. So this will be equal to the fourth root of 2 times 81 times x to the 8th times y to the 4th. So the fourth root of 81 is 3. the fourth root of x to the 8th, you divide your exponents. So 8 divided by 4 is x squared. The fourth root of y to the 4th, 4 divided by 4, is y. And my 2 has to stay inside the fourth root. When you add radicals together, like in 26, the only way to add two radicals together is if they have the same radicand. So if I factor this down, this is 2 times 16, and the square root of 16 is 4. So this is 4 square root of 2. Plus 200 is 2 times 100. So the square root of 100 is 10, and the 2 stays inside. Once you have the same radicand, you can add the two together, like combining like terms. So this becomes 14 square root of 2, where you add the two coefficients together, but the radicand stays the same. In number 27, we have the cube root of negative 8 raised to the third power. Well, this means the cube root of negative 8 times the cube root of negative 8 times the cube root of negative 8. The product rule says that we can put all three of those under the same radical. So this is the cube root of negative 8 cubed. Well, using the nth root of the nth power, this is going to be negative 8 because the index is odd, n is odd. So we take the value of a inside. Number 28, the square root of 9 squared. So this means the square root of 9 times 9. Well, the square root of 9 times 9 is the same as the square root of 81, which is just 9. Number 29 is very similar to 25. We just have to remember that odd indexes can take the root of negative numbers. So the cube root of negative 81, we need to factor this down just a little bit. So this is going to be negative 1 times 81. 81 is going to factor into 3 times 27. 27 is a perfect cube because it's 3 times 3 times 3. So I can take the cube root of 27, and negative 1 is also a perfect cube. And since both of my exponents on my variables are divisible by 3, those are also perfect cubes. So my cube root of negative 1 is negative. My cube root of 27 is 3. The cube root of x cubed is x. The cube root of y to the 6th is y squared. And this 3 has to stay inside of my cube root. In number 30, we have the square root of 25x to the 4th over the square root of 81. Now, if we use the quotient rule to separate these two into two separate radicals, it will make our math easier because independently, these two are perfect squares. So this becomes 5x squared over 9. Similarly, in number 31, if we separate these two, it makes our math a little bit easier. So I have the cube root of 16x to the 4th y cubed over the cube root of 125. So 16 is not a perfect cube, but 8 is. So this will factor into 2 times 8. The 2 will stay inside, but the 8 will come out. X to the 4th is not a perfect cube, but x times x cubed is equivalent, and x cubed is a perfect cube, and the x will stay inside with the 2. So I have the cube root of 8 is 2, the cube root of x squared is x, the cube root of y cubed is y, times the cube root of 2x that stays inside, over the cube root of 125, which is 5. In number 32, we're multiplying two radicals together. Independently, they are not able to be simplified because we're taking the fourth root of each one. But using the product rule, if I combine them under the same radical, I have 3 times 27 is 81, and x times x cubed is x to the fourth. So by combining them under the same radical, they become a perfect fourth. And this is equal to the fourth root of 81 is 3, and the fourth root of x to the fourth is just x. When you factor 112, if you attempt to factor it into 2 times 56, neither one of those are perfect squares, and 3 won't divide it. But if you factor it into 4 times 23, the 4 becomes your perfect square. X is not a perfect square, and y can be factored into y times y to the fourth power, where y to the fourth power is a perfect square. So this will simplify into the square root of 4 is 2, the square root of y to the fourth is y squared. But the 23 and one of the y's will have to stay inside the radical. With 34, we have a cube root. Well, 12 can be factored into 2 times 6 and 2 times 3. There is no cube root, perfect cube, that exists inside of 12. X to the fourth can be factored into x times x cubed, so it has a perfect cube, but y squared does not. So this simplifies into the cube root of x cubed is x, and the 12, one of the x's, and y squared must stay inside. In 35, similar scenario as in 32, where independently this can look rather complicated. But if I will combine them underneath the same radical using the quotient rule, then I can simplify things down very quickly, and it makes my math easier to manipulate. So 2 over 8 is going to become 1 over 4. The x cubed over x is x squared. The y over y cubed is y squared on the bottom. So now all of these are perfect squares. The square root of x squared is x, the square root of 4 is 2, and the square root of y squared is y.